Hi everybody, welcome back. This is where we left off in our last video. So in this new series of videos on categorical or binary dependent variables, so outcome variables. So we ended with a little example here where we're modeling the effect of student loan or the association between student loans and self-employment. And so again, what we have here is the outcome variable is going to be made up of ones and zeros. And in this case, we're doing the linear probability model. And so we just build out a normal ordinary least squares OLS regression. And we could end up having some estimated beta, which would be the association between student loans and self-employment. And suppose if that's negative 2%, then a $1,000 increase in student loans is associated with a 2% decrease in the probability of self-employment. And so I guess, technically maybe these need to be measured in thousands. So anyway, okay, so this will work. It'll give us some estimates. We can do normal ordinary squares, and that's kind of by definition the linear probability model, linear in parameters, just as OLS is. But there are going to be a few problems when we do it this way. So let's talk through those, and this is going to ultimately lead us to the conclusion that we need a different type of model, and that's where we're going to end up with Logit or Probit model. So let's start out with some of these problems. First, the error term is not normally distributed. The error term is not normally distributed. Okay, and that was one of the assumptions we talked about when we talked about ordinary least squares. And because of this, because the dependent variable can only take on two values, 0 or 1, the error term is not normally distributed, but it has a binomial distribution. So I'm going to write that down. Because the dependent variable can only take on two values, right? Either a 0 or a 1, because the error term ultimately, you might say that some person y1 is they have a 1 for an outcome, but if you're wrong about that, then the error is 1. So if you say it's going to be a 1 but it should be a 0, you're off by 1. If you say it's going to be a 0 but it's a 1, you're also off by 1. And anytime you're right, if it's a 1 and you say it's a 1, your error term is 0, and so on and so forth. So in any case, your error term, as a result of this phenomenon, the error term has a binomial distribution. Okay, so that's one of the problems. And I should note these first three problems that we're going to have, they're not going to be huge big deals, but the fourth one will be. So in any case, second one is that the error term is heteroscedastic. Okay, and so again, going back to several videos, many videos ago, when we talked about that, that's when the variation of the error term changes depending on the y variable, the value of the y. So in any case, that one, it can also be fixed using this idea of robust standard errors. But moving on to the next one. Also, not a giant deal. R squared is not a good measure of fit. But we could use other measures of fit if we wanted to do this. So that one's not a big deal either. But we do have this unboundedness problem. And this one is going to be a little bit of a bigger deal. So let me explain a little bit more about this. So remember, we're going to use this simple model where di is our indicator variable, the theta 1, x1, plus the error term. So the estimated value of di which is going to be di hat, which is a probability, is not necessarily bounded by 1. By 0 and 1. Okay, but the reason that's a problem is that, but probabilities are bounded by 0 and 1. And to kind of make this point a little bit more clear, let me show you an example graph. So let's suppose that we're modeling, sorry for drawing through the lines, let's suppose that we're modeling whether or not somebody is retired. And here's 0, and let's say here is 1. And we could look at the relationship between age and whether or not somebody is retired. And so let's start here at 30, 40, 50, 60, 70, and 80. Okay, and now let's make some data. All right, so let's say that our first person, they are 25, and they are not retired. There are going to be a bunch of other people here who are young and retired. There might be some like very young, wealthy 30-year-old, and they're going to pop up here and be retired. So there's somebody up there who's retired. But by and large, there are only going to be a few young people who are retired. In the 50s, we might start getting a few more. And it's going to start tapering off. So as people get older, 65, actually let's just keep a pretty wide range until 65. More people start retiring early. And then there are going to be a few more people. So basically a huge amount of people here. And it's going to start tapering off. Might have some people in their 70s still working, a couple in there as they move on. Working until they die. But once we start getting into 65, we're going to start seeing a huge number of people retiring, getting the Social Security checks, and we're just going to have a huge amount of people there as well. Okay, and remember, we're still dealing with a linear probability model, which is ultimately just OLS, ordinary least squares. And so we're trying to find a line that minimizes the sum of squared residuals as before. So, we could have a line here, but we're going to have loads of residuals here and loads of residuals here. If the data are primarily concentrated in these two places, the best fit line might look something like this. Okay, because ordinary least squares, again, is just a line with an intercept and a slope. Okay, and so in this case, the intercept might be down here. Let's call it negative 0.1, which is negative 10%. All right, and this line could go up as high as over here we have, let me actually, well, there's our intercept, beta 0 hat, because it's our estimate. Let's say the slope is beta 1 hat. Let's call it, I don't know, let's just call it, this is a completely arbitrary number. Let's call that 0.25. Probably needs to be much lower than that. Let's say 0.02. So then every year older you get, there's maybe a 2% increase in the probability of retirement. But what's going to end up happening is, if we want to predict where somebody's going to retire, the probability of somebody retiring, then let's take any given age. So let's say 52 or 53. At that age, we come up here and we're going to predict that the probability of retirement when you're 53 is, say, 25%, right? And then you come up here and let's say at 70, I don't know, 78, the probability of retirement is 100%. The problem, and this is the unboundedness problem, is that if you're 30, no, let's say whatever this number is here, let's say that that's 20 years old. If you're 20 years old and you're down here at the intercept, your probability of retirement is negative 10%. And if you're 80, no, let's say you're like 80, let's say you're 90. At 90, your probability of retirement is, say, 115% for a 90-year-old. That's a problem because 115% and negative 10%, those are not probabilities. That's mathematically impossible. So this linear probability model doesn't have a way to prevent these, at least at the basic level, doesn't have a way to prevent these unrealistic and impossible probabilities of existing. So this is demonstrating this unboundedness problem. Theoretically, these probabilities should be completely bounded between 0 and 1. And the linear probability model is just not going to do that for us. So, that's not mathematically possible. As I was saying before, those first three problems, the normality, the heteroscedasticity, and what was the other one? The R squared, those can be fixed. Problems 1 through 3 can be addressed relatively easily. Can be addressed relatively easily, but the better approach is to use a nonlinear estimation technique. So, nonlinear estimation technique, which is departing from everything we've been working up towards so far. And this will solve the unboundedness problem. Okay, and that nonlinear estimation technique that we're going to be using is called the binary Logit model. Okay, or we'll talk a little bit about it, but they're largely the same. The binary probit model. Okay, and what's we're gonna carry that on in another video, in the next video. But if we had the same situation here with age and retirement, and we have 0 and 1, and we have 0 and 1, what the binary Logit or probit models are going to do is that it's going to model the probabilities based on the logistic or the normal probability distributions, and what that's going to lead to is boundedness. So a Logit distribution is going to be bounded asymptotically by 0 on the bottom and 1 on the top. And that's going to be able to solve our problems so that maybe the probability of that 25-year-old is going to be 0.01%, right? And the probability of a 90-year-old not being retired is 99.9%. And so that's just going to help. That's going to help, solve the unboundedness problem. Okay, so that's where we're going with this, and that's what we're going to be chatting about in the next video. Thanks for watching, and I'll see you then.